everybody. I'm Vadim. I'm the head of the ANPL lab, Autonomous Navigation Perception Lab. And in the lab, we develop new approaches for decision making under uncertainty and for autonomous perception and inference. So to motivate this short talk, we are kind of motivated by applications that you see here on different autonomous agents in the wild, autonomous driving, medical applications, space, and so on. And in these applications, the agents are actually required to exhibit quite advanced capabilities, such as autonomously decide how to sense the environment, how to gather information, how to navigate autonomously without colliding. And in some cases, for instance, in this case, it is really important to provide guarantees that the probability of collision is sufficiently small such that this 1 billion agent is negligible, for instance. So this is the motivation for our research. And in the lab, we develop advanced autonomy capabilities and perspectives. On the one hand, we deal with perception and probabilistic inference, such as SLAM, for instance, where we are trying to perceive the environment based on noisy data that comes from sensors. And this perception part can be on a geometric level, meaning what is the XYZ position of different entities, landmarks, pedestrians, so on. It can be also on a high level, semantic perception, meaning what is the class of this object? Is it a bicycle, a cat, a car, and so on. Can be also on the level of occupancy grid. So this is basically the idea of getting data and coming up with a probabilistic presentation that that basically tells us what is the probability of some of the state of a certain label. So this can be either continuous, discrete, or a mix of labels. On top of that, we really deal with decision making under uncertainty, considering partially observable domains, what is known as Philips planning, or partially observable Markov-Decision processes, ODPs. And in this part, we are investigating techniques for the agent to autonomously decide its next actions or policies. So just to be a bit more specific, let us consider this very toyish example where we have a very simple agent, and we have this reward, and the agent has to be in one of those cells, right? It doesn't know which cell is located. And the agent, via probabilistic inference, maintains a distribution over its possible locations. So each bar here represents the probability to be in some specific cell. And this distribution is being updated with data. Okay? So as more data comes in, actions, observations, so on, we update this. And now imagine if we want to plan now in this setting. So in our case, planning actually involves reasoning how the distribution would evolve into the future for different possible actions and for different possible observations. But generally, the distribution will evolve differently for each such combination. So you can appreciate that when you construct such a tree, it is computationally intractable to actually go over all the possible possibilities here. You cannot do this in practice. And especially when we consider high-dimensional settings, such as in SLAM or high-dimensional sensors, images, and so on, cannot really go over all the possible observations, all the possible images. So the question that we ask in the lab is how still, despite these challenges, can we develop approaches to act autonomously and reliably in an online setting and perform those advanced tasks in a safe manner. So this is kind of the vision that we have in the lab. So among the different directions that we have in the lab are, I listed some that's here. So for instance, one direction, we focus on how to properly integrate experience within planning. In other direction, goes into multi-agent inference, how to collaborate with agents, multiple agents, how to do planning as a group. Another direction investigates risk-averse and safe decision-making under uncertainty. Yet another direction looks into semantic perception, semantic slang, how to do this autonomously. And another direction that I want to mention now, that we're focusing now, is trying to simplify the decision-making problems while providing formal performance guarantees. So let me take a few moments to describe this specific direction as an example. So over the years, we introduced this new idea that I'm still very much excited about it. And the idea is that we want to speed up, to accelerate the online decision-making process by taking the original problem that is very difficult to solve, as we saw before, and coming up with some easier, smaller problems. So breaking it down to some smaller problems. If we can do that, the idea is to somehow relate between the original and the simplified problems. And this relation often is done by developing formal guarantees in terms of heuristic bounds or heuristic bounds. Once we have such a capability, then we can consider how to do adaptation, meaning how do you detect online on which level of simplification can we use this. So sometimes if the problem is difficult, we might need to get back to the original problem. But in some cases, maybe it is sufficient to abstract many details and still provide the optimal solution at a fraction of the compute time. And this comes with formal guarantees, so we are sure that the solution is optimal or close to optimal. So over time, we developed different perspectives of this framework. For instance, we investigated this for non-terminative beliefs, where the simplification is realized by considering only a subset of samples. So let's say instead of 1,000 samples, what happens if we only consider 10 samples? What can you provide? What can you say about this observabilities? Another instance, we investigated simplification of learned models. For instance, the models could respond to some deep networks that are, have many parameters inside. What happens if we take a smaller network with much less parameters, so much easier to query? You can do that, but what kind of guarantees can you provide? And we have a poster with the DOM that deals with that later here, if you want to look later. And what I want to finish today now is with a glimpse into one other subdirection here that looks into simplification of multi-agent systems. And in this direction, we ask the question, what happens if we have a bunch of agents and these agents cannot really share all the data that they have with each other? Why? Because they have communication is costly, maybe they do not want to communicate everything, whatever is the reason. So imagine these two agents that cannot share the observation that they just obtained. And as a result, this agent misses the sound observation that agent has, and vice versa. Since these agents do not have the same data, their distributions for the state become different, because it is conditioned on different data, different histories, because they didn't share it. And generally, it can be shown that such a setting where the distributions are different can lead to lack of coordination, can lead to catastrophic events, and generally just suboptimal performance. And so the challenge that we investigate here is how to guarantee a consistent joint action selection by this group of agents, despite having inconsistent histories. And when it is not possible, how to come up with a proper way to communicate the relevant piece of information that will allow us to provide such a piece. So this is one other direction. And then let me also, In the lab, we also have activities related to oh, it doesn't work. Okay. There's supposed to be an amazing movie here that you will not see now. Okay, next time. But matching quads, flying, and doing very advanced things. We have robots, application of playing games with the algorithms that we develop. And we are actively looking for amazing students. Thanks.